Chapter 6 Periodic Table 6.2 Periodicity Part 1. At the end of this lesson, you should be able to describe the variation in atomic radii across period 2 and 3 as well as down the group 1 to 13 to 18. The explanation will include the effective nuclear charge and shielding effect. Next, you should be able to compare the atomic radius of an element and its corresponding ionic radius. However, this will exclude the comparison of radii for isoelectronic ions. This is the periodic table of elements. We have group 1 to 18 and period 1 to 7. In general, the atomic radii decrease across the period, but the atomic radii increase down the group. There are two factors affecting atomic radii. The first one is effective nuclear charge, or ZEF, and the second one is shielding effect. Across the period, effective nuclear charge, or ZEF, is the factor that will affect the atomic radii of elements across the period. Effective nuclear charge is net positive charge experienced by the valence electrons. To calculate the effective nuclear charge, you need to minus the nuclear charge or proton number with the number of inner electrons. Number of inner electrons is electrons that resides in inner shells. This is how you calculate the effective nuclear charge. These are the elements in the period 2, and this is the electronic configuration. The inner electrons are the electrons that fill the 1s orbital in each element. Therefore, as you can see here, the inner electrons are 2 throughout all the elements in period 2. To calculate the effective nuclear charge, we just minus the proton number with the inner electrons. Therefore, you will find out the value of the effective nuclear charge. As you can see, across the period, the proton number will increase, as well as the effective nuclear charge. This is similar to period 3 elements. However, they have more inner electrons because these are the inner electrons. So the effective nuclear charge is the proton number minus with 10 for each of the elements in the period 3. Remember that elements in the same period have the same number of shells filled with electrons. Therefore, their sizes depend on the effective nuclear charge, or ZEF. Higher effective nuclear charge will result to smaller atomic radii. This is the general variation in atomic radii across the period 2. As you can see, lithium is the biggest, while neon, on the right hand side of your periodic table, is the smallest. Across the period 2, from left to right of the periodic table, proton number increase. This will result to effective nuclear charge increase as well, and the attraction of nucleus towards the valence electron becomes stronger. Therefore, the size of atom decrease across the period. The general trend of decreasing size of atom is still the same across the period 3. So as you can see here, sodium on the left hand side of your periodic table is the biggest, while the argon, which is on the most right hand side of your periodic table, is the smallest. Again, the explanation is similar to the previous slide. In the exam, if the question asks you to compare atomic radii of two elements, you cannot explain in general terms. However, you need to be more specific. In example, if we compare sodium with aluminium, you need to write down the electronic configuration first so that you can calculate the effective nuclear charge. Be reminded that sodium and aluminium is in the same period, which is period 3. Therefore, they have the same number of shell. The only factor that will affect the atomic radii is effective nuclear charge. Whichever have or has higher effective nuclear charge will be smaller than the other one. So, since aluminium has higher proton than sodium, the effective nuclear charge of aluminium is higher than sodium. Therefore, aluminium will have a stronger attraction of nucleus towards the valence electrons compared to sodium. Therefore, aluminium has smaller size of atom than sodium. Now, we move on to the trend of the atomic radii down the group. Down the group, shielding effect will play a bigger role in determining the size of atoms. Electrons in an atom can shield each other from the pull of the nucleus. This effect, called the shielding effect, describes the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. This means that more electron shells there are, the greater the shielding effect experienced by the outermost shell. As you can see here, the higher the number of shell contained by your atom, the bigger your atomic radii becomes. This is due to the shielding effects, which increase with increasing number of shell. Let's have a look at the variation in atomic radii down the group. These are elements in group 1. Based on the electronic configuration, we can determine the number of shells filled with electron. Hydrogen only has one shell filled with electron, while lithium has 2, sodium has 3, and potassium has 4. So, we can conclude that down the group, shells filled with electron increase, which in turn increase the shielding effect. Since the shielding effect increase, what happens is the attraction of nucleus towards the valence electron becomes weaker. You have to remember that if shielding effect increase, attraction becomes weaker. Therefore, the size of atom increase or becomes larger down the group. If the question asks you to compare atomic radii of two elements, again, do not state the general statements. You need to be more specific for the given elements. In example, carbon versus silicon. Carbon and silicon are both in group 14. This is the electronic configuration of carbon and this is the electronic configuration of silicon. Therefore, based on the electronic configuration, we can see that carbon has 2 shells filled with electrons, while silicon has 3 shells filled with electrons. Therefore, silicon has more shells filled with electrons compared to carbon. What happens is, silicon will have higher shielding effect than carbon. Since silicon has higher shielding effect than carbon, silicon will have a weaker attraction of nucleus towards the valence electron than carbon. Therefore, silicon has a bigger size of atom than carbon. Atoms versus its corresponding ion. Atom versus cation, a positive ion. To form cation, atom remove electrons from its outermost shell. This decreases the number of shells filled with electrons. Therefore, since the number of shells filled with electrons decrease, the shielding effect will decrease as well. So as you can see here, magnesium atom is bigger than its cation, which is magnesium 2+. To explain this, magnesium versus magnesium 2+, here is the electronic configurations for both magnesium and magnesium ion. As you can see, magnesium atom has 3 shells filled with electrons, while magnesium 2+, which is its cation, has 2 shells filled with electrons. So, magnesium has more shells filled with electron than magnesium 2 plus. What happens is magnesium will have higher shielding effect compared to magnesium 2 plus. Since the magnesium has higher shielding effect, magnesium will have a weaker attraction of nucleus towards the valence electron compared to magnesium 2 plus. Hence, magnesium has bigger size than magnesium 2 plus. So in conclusion, magnesium is bigger than magnesium 2 plus, or any atom compared to its cation will have a bigger size than its cation. What about atom versus anion, which is a negative charge atoms? To form an ion, atom gain electrons into its outermost shell. The number of shells filled with electron remains. No additional shell is added when electron is added into the atom. However, when electron is added to the outermost shell, mutual repulsion within the shell increase, expanding the shell. As you can see here, one electron is added into the existing shell and it will repel each of the electrons inside the shell. What happens is the shell will expand and making the anion bigger than its atom. As you can see, we can conclude that atom is smaller than its corresponding ion due to mutual repulsion. This is different from atom versus its cation. To explain this, first of all, write down the electronic configuration for the chlorine and chlorine minus. As we can see here, both chlorine and chlorine minus still have the same number of shells filled with electron, which is 3. Therefore, shielding effect will not play a huge role here. Since chlorine gains 1 electron into its outermost shell from chlorine to form chlorine minus, this will increase the mutual repulsion within the same shell. Mutual repulsion meaning that the electrons in the shell repels one another, making the shell expanded. Thus, Cl- has weaker attraction of nucleus towards the valence electron than chlorine due to the shell expanding. Hence, chlorine minus has bigger size than chlorine atom. Quote of the day: it's kind of bittersweet. The human spirit is not measured by the size of the act, but by the size of the heart. Yakov Smirnov. Before we end the video, let's try some exercise. You may pause the video first and try the question first and then check your answer. Exercise number 1. This is the answer for exercise 1. Now let's try exercise number 2. And this is the answer for exercise 2. Thank you for paying attention.